Hello, everyone. This is going to be a lesson for Calculus 1 about the first derivative test. So recently we've been learning about the maxima and minima of a function and how to find them. And we learned about what that has to do with the derivative, right? Because the derivative is used in finding critical points. So this lesson is going to continue that discussion. It's called the first derivative test because we're going to use the first derivative to help us figure out what a function looks like. Maxima, minima, and some other things. Okay, so let's go ahead and see what we can do. All right, so this is called the first derivative test. And you might be wondering, does that mean there are going to be other derivative tests? Well, basically, this lesson is about what does f prime say about f? So when we say the first derivative test, we mean we're going to be using f prime. And in a following lesson, I think the next video lesson that you see, we're going to look at f double prime. So that will be a separate story. But for now, it's what does the first derivative tell us about a function? Well, one thing that we can say, remember that I gave you a definition sheet last time with some definitions from these sections. So I'm going to go through some of them pretty quickly because they're already on that sheet. But when f prime is positive, f is increasing. And when f prime is negative, f is decreasing. So what do we mean by increasing and decreasing here? We mean if you were to graph it and look at the function as you go from left to right, this first function would be going kind of on an upward trajectory. And the second function, if you went from left to right, it would be going downward. That's what we mean by increasing or decreasing. And this makes sense because the derivative, f prime, is supposed to tell us the slope of the tangent line. So if the slope is positive, we know that a positive slope means we're going upward. And if the slope is negative, we know that a negative slope means we're going downward. I've got some little examples for you here. I think I have 3 of these. I'll do some of them and then I'll ask you to do one. So let's determine intervals of x values where f is increasing and where it is decreasing. And I'm going to write 3 different functions. I think I'll do the first 2. I'll just write all 3 functions here. F of x equals 3x plus 1. F of x equals x squared minus 4x plus 7. And finally, f of x equals 1 minus 4x minus x squared. Those are the 3 we're going to do, but I'll do the first 2 for us. All right, so if we're given the function 3x plus 1, if we want to follow what's said above about f prime being positive or negative, we could very quickly find the derivative of this function, right? The derivative of 3x plus 1 is just 3. So, for different x values, like imagine putting in different x values now to f prime of x is 3. It seems like no matter what x value I put in, f prime is always going to be 3. F prime of a million is 3. F prime of negative a million is 3. It's a constant, right? It's a constant function. So 3 is positive. 3 is positive. So a positive slope means that f is increasing everywhere. So what interval should we say that it is increasing on? I'm going to use the word on. We say it's increasing on the interval, in this case, negative infinity to positive infinity. And this function is never decreasing. So, yeah, that's an example of a function that is increasing for all real numbers. Slope of the tangent line is positive at any real number. The next one, let's see if the next one might be more interesting. X squared minus 4x plus 7. So let's find the derivative and let's see what it tells us. So the derivative, we can find these really quickly now, right? 2x minus 4. All right. Now, where is this positive and where is this negative? When is 2x minus 4 positive? Question mark. And when is 2x minus 4 negative? Question mark. Let's figure these out. Because that's going to answer when the function is increasing or when the function is decreasing. These are just two little inequalities. We could like add 4 to both sides, divide by 2. So that's my answer to that. And then over here, add 4 to both sides, divide by 2. But I think that the problem said determine intervals of x values. This is not written as an interval. We want to use interval notation. Curved parentheses, square brackets, all that stuff. So let's say that based on what we found here, I think we can conclude that f is increasing on the interval. I want to say everything greater than 2. How do you write that as an interval? Curved parentheses 2, comma, infinity. That is the interval of x values that are greater than 2. It is decreasing on the interval. I want to say everything less than 2. How do we say that as an interval? Negative infinity, comma, 2. And that's the answer. So we found that this function is increasing on a big interval and decreasing on a big interval. Maybe we could draw the number line and imagine it that way. It seems like at 2 something is happening. Something special is happening at 2 where the function switches from decreasing to increasing. We'll talk about that in a few minutes. Like if we were to graph this, I think we would see something is happening at x equals 2 when the switch occurs. Although I guess part A didn't have anything like that. All right, so I want you to try part C. I'm going to write the function again. So determine intervals of x values where f is increasing and where it is decreasing. And the function is this. So I'd like you to pause the video and give that a try. Okay, first thing you should have done is find the derivative, because we're going to need that. So what? Negative 4 minus 2x? Okay. Let's answer this the same way as we did for part B. Let's look at when is this thing positive, because that's when the function will be increasing. And when is this thing negative, because that's going to be when the function is decreasing. If it is decreasing ever. We'll figure out. All right, so what do we do here? Should we add 4 to both sides? Let's do that. Add 4 to both sides. You can do that over here too. Divide both sides by negative 2. Be careful. You've learned from algebra that when you have an inequality, if you divide both sides by a negative number, it flips the inequality symbol. Same thing here. It's okay to divide both sides by a negative number. But yeah, if you divide or multiply both sides by a negative quantity, it flips the inequality symbol. It's okay to do it as long as you flip the sign. Remember, this is where the function is increasing, and this is where the function is decreasing. But don't just leave your answer like this. it said in the problem, it used the word intervals. That means you need to write your answer as intervals. So answer, I think that this function is increasing on the interval. How do we write everything less than -2? That would be negative infinity, comma, -2. And it's decreasing on... How do you write an interval for everything greater than -2? It's going to be -2 to infinity. Remember, when you write intervals, you write curved parentheses if the number is not included in the set. You write square brackets if the number is included in the set. We always do curved parentheses next to infinity or negative infinity because those are not numbers that can be included in a set. And when you write an interval, always make sure that the smaller quantity is to the left. -2 is on the left because infinity is the bigger one. All right, so that was just a couple of problems about figuring out when a function is increasing or decreasing. We've got a little more to say. When f prime switches from positive to negative, I was about to write something, but I just realized I need to add a little disclaimer to this, but I'll write it and then I'll add a little disclaimer. All right, so if we switch from positive to negative, f has a local maximum. Right? Because the function was increasing, and then it's decreasing. I'm going to write a disclaimer, but I have one more thing to write first. When f prime switches from negative to positive, f has a local min because we are decreasing and then we get to a point where it switches to increasing. My disclaimer off to the side for both of these is I'm going to say as long as f is defined at these points. All right, so if we had, there are a couple of exceptions, but in general, if you're dealing with something where the function exists at the place where it switches, it's going to be a local max or a local min. If it's not in the domain, well, if it's not in the domain, we can't say there's a local, we can't say that f attains a local maximum at a certain value if the function doesn't even exist at that value, right? So yeah, as long as it's defined, then these statements work. So this is pretty cool. This means that, like in those previous examples when we found the intervals of increase and decrease, like for example, the one that's still on the screen, it seems like something interesting is happening at -2. If you were to kind of read this from left to right, from negative infinity to -2, the function is increasing. Right, the function is going upward. It could be curved. I'm drawing this as like a straight diagonal line, but it can be curved but going upward in some way. And then here it's decreasing. Well, guess what? This is a parabola, isn't it? Isn't this a parabola that opens downward like this? So it makes sense that the function is increasing for part of it and then switches to decreasing for part of it. What we found is the place that is a local maximum. Looks like there's a local maximum at x equals -2. So here's the key idea. we can use f prime to find intervals on which f is increasing or decreasing. And use this to find local maxima and minima of f. Now, we did a little example a few minutes ago where we found intervals of increasing and decreasing, and we did this by basically using the idea of f prime being positive or negative. So we set up little inequalities. Inequalities can be a little tricky to work with, especially like that one where we had to flip the inequality symbol because we divided by a negative number. So I'm going to show you that we have kind of a process or a strategy that we follow where we won't have to deal with the inequalities so much. So I'm going to show you, work through like an entire example with this new strategy. And I think you'll like it because we don't have to deal with messy inequalities. And it's still going to get us the same results. All right, given this function, on what intervals of x values is f increasing, decreasing, and then it's also going to say find the x coordinates of local maxima and minima. And of course, this always means if there are any. Even if a problem doesn't say that, it means if there are any. I'll walk us through this. You know that a function could sometimes just be always increasing. It doesn't have to have maxima or minima. We'll see what this has. Also, when we talk about maxima and minima, we could just combine those two words and say, find the x coordinates of local extrema. And it would mean the same thing. So I said that there's kind of a procedure or strategy. And actually, I'm going to break this down into 4 steps. I could tell you these 4 steps first, but I think for this, it's nice to just show you in a problem. Okay? Step 1 is going to be find f prime and critical numbers. You remember what critical numbers are from the previous lesson. We sometimes call them critical numbers. We sometimes call them critical points. Same thing. Let's do this step. We'll do each step as I explain it. So f prime, look at the original function and find the derivative of it. 3x squared minus 3. We notice that, remember, to find critical points, you either set this equal to 0 or you find places where this does not exist. But, I'm just going to say this always exists for all real numbers. So I don't see any critical points coming from that direction. But we could set this equal to 0 and see what we get. By the way, when we were given this function, it didn't tell us a domain. You know that we had some problems where the domain was given as like a closed interval. This didn't give us the domain. So if it doesn't give you the domain, then you just assume it's the standard domain for this polynomial. And it's a polynomial, so the domain is all real numbers. The domain of this is also all real numbers because it's a polynomial. So let's just take this and set it equal to 0 and solve, because that's how we're going to find critical numbers. Let's How about we divide everything by 3? You can't do that in the previous, like f prime of x is this. You know what I mean? Like if I divided by 3, I'd be changing it. It wouldn't be f prime anymore. But now that I turned it into an equation that I'm trying to solve, I could do whatever I want to it. I'm going to divide everything by 3. All right, so x squared equals 1. So x equals -1 and x equals 1. If this were one of those problems where we had like a specific domain that was given to us, we would have to check to see like, are these in the domain or not? But the domain is all real numbers, and these are real numbers. So these are both critical points, critical numbers. I guess above I called them critical numbers, so I'll call them that here. That's it for step 1. Step 2 is going to be something new for us. We're going to set up a kind of chart, and it's called a sign chart. So I think what I'll do is I'll draw it and then I'll kind of explain what it is, but it's going to be a portion of the real number line. I'll write some of this. A portion of the real number line with the critical numbers labeled. We'll use this to organize results we find. All right, that's going to make more sense once we actually do it. But you know that the real number line includes -1 and 1, so just make sure -1 is somewhere to the left and 1 is somewhere to the right because it's bigger. And don't label any other numbers. The real number line also includes 0, which is in the middle here. It includes 2, which would be over here, but don't label any of those. Only label the critical numbers. And there's one other thing that we usually do with these sign charts. Over here, I'm going to write f prime of x, and over here, I'm going to write f of x. This is to keep track of what's the function that we're working with. We're working with the function f of x, and what's the derivative we're working with? F prime of x. That's it for step 2. Step 2 was to draw this. This is going to be a 4-step process. Step 3. Notice from the sign chart that the critical numbers partition the real number line into multiple intervals. Check the sign of f prime of x at one x value for each interval in the sign chart. Here's what I'm going to do, okay? Because ordinarily, when we're doing these problems, we're just going to draw one sign chart and we're going to like add information to it. There's space here for us to add information as we find it. I said we're going to use this to organize the results we find. So we would be writing stuff in steps 3 and 4, mostly in step 4. We're going to write some stuff on here. But because this is the first time we're doing this, I'm actually going to draw more than one sign chart just so that I can point out the things that I'm saying. All right, so here's what I mean when I say notice the sign chart. Notice from the sign chart that the critical numbers partition the real number line into multiple intervals. Here's what I mean. This stuff right here, this right here, and this right here. It's like 3 different intervals. This would be 1 to infinity. This would be the interval -1 to 1. And this would be the interval -infinity to -1. So the critical numbers are chopping up the number line. And because there were 2 critical numbers, we actually have 3 intervals. Now, the next sentence says, check the sign of f prime of x at one x value for each interval in the sign chart. So these are the 3 intervals. So I need to check f prime of x at one number from each of these intervals. Now, it doesn't tell us what number to check. And the answer is, it's up to us. Oh, by the way, remember, because we kind of moved it off the top of the page, that f prime of x for this problem was 3x squared minus 3. So let's check f prime at one number from each of these 3 intervals. And we're going to figure out if it's positive or negative, because it says to check the sign. From this first interval, -infinity to -1, we need to pick a number. We get to choose. Now, I'll tell you one thing we're not allowed to choose. We're not allowed to choose -1. Because -1 is not in this interval. It's a curved parentheses. That means -1 is not included, right? Look at the number line. It's everything less than -1. So pick any number you want in this interval as long as it's less than -1. I think that you can try to find like integers. They're going to be easier to work with. I decided to check -2. I thought that would be the easiest thing to check. And we put that into f prime, so we do 3 times -2 squared minus 3. That's going to be 3 times 4 minus 3, so 12 minus 3 is 9. What is the meaning of 9 in this context? What do you think? It's the slope of the tangent line at that specific point, right? What this is telling us is that the sign is positive. And we're going to make note of that more in step 4, but let's move on and check the next one. We need something from this middle interval. It goes from -1 to 1, but we can't actually use -1 or 1. We have to use something between them. So what's a good number in between them? I think 0. 0 is a real number in between them, and it's going to be easy to put into this. 3 times 0 squared minus 3. To try to pick easy numbers. I mean, if you wanted, you could check 1/7. You'd have to do 1/7 squared and all that. You're going to get the same result, positive or negative, but you might as well pick easy numbers. I got -3. What we really care about is that what I got is negative. And then finally, we need something from this third interval. It has to be greater than 1. I'm going to pick 2. I think that's the easiest number to work with here. If you pick something like 3, that's fine. Maybe you could pick something like 10, because it's easy to do 10 squared. 10 squared is 100. So, you know, there's other options. 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. Minus 3 is 9. So it's positive again. Okay, I said there were going to be 4 steps. We just finished step 3. Maybe at this point I should remind you, what are we trying to do in this problem? Because we've gone over a page here. So before we do step 4, real quick, Let's just take a quick look at what the problem was. It gave us a function. It says on what intervals of x values is f increasing, on what intervals is it decreasing, and find the x coordinates of any local maxima or minima. So it's really four things we want. Intervals of increase, decrease, x coordinates of maxima, minima. All right, we're going to try to find all of that and put a big box around it at the end. So step 4 is going to be based on the results of step 3, fill in the sign chart. I have to show you how we do that. And deduce answers. So remember the sign chart we drew in step 2. I said something earlier about how typically in a problem we would only draw one sign chart for a problem, but I'm drawing 3 of them because we're discussing it for the first time. This is what the sign chart originally looked like in step 2 before we drew anything else on it. So this is what we have. And what we found in step 3 was that in the first interval, f prime was positive. And the way that I'm going to indicate that on the chart is I'm going to just put a plus sign here. In the second interval, f prime was negative, and I'm going to indicate that with a minus sign. And in the third interval, f prime was positive, and I'm going to write a plus sign to indicate that f prime goes positive, negative, positive. Underneath, I'm going to write what's happening to f of x. Well, when f prime is positive, f of x is increasing. When f prime is negative, f of x is decreasing. And when f prime is positive again, f is increasing again. That's all. That's the completed sign chart. Okay? Completed sign chart for this problem. And now we can write our answers. We can deduce answers based on this. Can you see where it's increasing and decreasing and where the local maxima and minima are? So, answers. F is increasing on, it said to find the intervals of increase and decrease. They're kind of encoded in this sign chart. We want to actually write them as intervals. So we wrote the word increasing because f is increasing on this first interval. That was negative infinity to negative 1. And also this third interval, that's 1 to infinity. We have more to explain. F is decreasing on this middle interval. That's going to be negative 1 to positive 1. And now we need to say, it says find the x coordinates of local maxima and minima. So I'm going to say, can we figure that out based on this? Do you remember what I said earlier? I said that we have to go back and look at this. When f prime switches from positive to negative, f has a local max. When f prime switches from negative to positive, f has a local min. Okay? You have that in your notes. Look at the sign chart. You can very quickly tell where does it switch from positive to negative. Just read it from left to right. It's going positive, 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 negative. The switch occurred at negative 1. So at negative 1, the function switches from increasing to decreasing. So there is a local max at x equals negative 1. Keep reading, just left to right to see what else happens. When we get to positive 1, the function switches from decreasing to increasing. So it was going downward and then it's going upward. So that means that there is a local min. at x equals 1. Now, that might be an absolute minimum, but we don't really know. Based on what we said here, we just know that that's at least a local max and a local min. But the problem only asked us for that. It didn't ask us for absolute max or absolute min. By the way, one other thing that these problems sometimes ask for, this one I guess didn't ask for it, but sometimes a problem might say find the critical numbers, and that would be included as part of the answer. So I'll just write them anyway. The critical numbers we found in step 1 were x equals -1 and x equals 1. So if you got like a multi-part problem, it might say part A, find the critical numbers. Part 2, whereas part A, find the critical numbers. Part B, where is f increasing? Part C, where is f decreasing? Part D, where are the local maxima? Part E, where are the local minima? So this kind of lends itself well to those kinds of problems. All right, I want to do another one, and this time I don't want to write so much because I wrote, a page and a half worth of explanation here, but this was us trying to understand this method for the first time. What's really cool about this method, though, is that we didn't have to write any inequality symbols. We didn't do any less than 0 or greater than 0. Inequalities can be tricky to work with. Instead, I really like this method where we just checked one value in each interval. And it's true that that's okay, because if you find that it's increasing somewhere in this interval, it's going to be increasing everywhere in that interval. Same for decreasing. Switches can only occur at critical points. And it doesn't mean that a switch has to occur at every critical point. This went increasing, decreasing, increasing. So there was switching back and forth, plus, minus, plus. But sometimes you might get a problem where it goes plus, plus, minus, or plus, plus, plus. It could be any combination. But we still check because the critical numbers are the places where it might switch. By the way, you know how I was saying that you could check any number, but you can't check like the actual endpoint of the intervals because they're not technically in the intervals? If you were to check what is f prime of -1 or what is f prime of 1, you'd get 0 because that's how we found them. They're critical numbers. So when you're in that step where you're checking values in step 3, you're trying to find, I'll remind you, we're trying to find, is it positive or is it negative? So you should never get an answer of 0 in this step. You should always get something that's clearly greater than 0 or clearly less than 0. And it doesn't even really matter what the number is, 9 or -3 or 100. It doesn't matter. You're just seeing, is it positive or is it negative? Because that's what goes on the sign chart, and that's what helps us figure out the answers. All right, let's have another function. How about this? I've been talking a lot, and I think I explained that problem in great detail. So how about I have you try this? Given f of x equals, and you can write a little less than I did, but I'd like you to try to do this with a sign chart. When I answer this, I'm just going to draw one sign chart, not like 2 or 3 of them. All right, you're given that function, and you want to find intervals of increase or decrease, if there are any, and x coordinates of local maxes and mins. So why don't you pause the video and take a few minutes to try to do this? So I'm going to go through this 4-step process, but this time I'm not going to label step 1, step 2, step 3, step 4. Let's just do it. Let's just go ahead. We know that we need to find the critical numbers, and to do that, we need the derivative. So let's find the derivative first. I guess 12x cubed minus 12x squared minus 24x. That seems like that's the derivative. The domain seems to be all real numbers for both f and f prime, so I don't think we're going to find any places where this is undefined. Maybe that's something that'll come up more in the next lesson. So we need to find where is this 0. Maybe it would help if we factor out a 12. You know, not only that, not only factoring out a 12, but we could factor out a 12x. Let's factor out 12x. Okay. Let's set this equal to 0. Set it equal to 0 and try to solve. You could divide both sides by 12, by the way. Oh, guess what? What's in parentheses here can be factored. I mean, you either have to factor it or use the quadratic formula, but who wants to use the quadratic formula? We don't have to use the quadratic formula. Like, don't use it unless you have to. That's my stance on the quadratic formula. If you can factor it nicely, then go ahead and factor it. All right, so it looks like I'm getting 3 different results here. X equals 0, x equals 2, x equals -1. Those are my critical numbers. Or I'll say critical points. I've been using those phrases interchangeably, but anyway. Before we move on to the next step, I just want to point something out. When you were at like this kind of step, and I said, let's divide both sides by 12, and I just got rid of the 12. You say, like, where'd the 12 go? I divided both sides by 12. So it's not here. And, you know, 0 over 12 is 0. It's okay to do that with constants. It's not okay to do that with variables. So, for example, if you got to this step and you said, I'm just going to divide both sides by x to get rid of it, and you crossed out x, that would be wrong because you would lose this information and you wouldn't actually find the critical point x equals 0. So don't divide by a variable like x. Don't get rid of a variable. And basically, the idea is that if you were to divide both sides by x, when you divide by something, you're assuming that it's non-zero. But x equals 0 is in the domain, and x equals 0 is a critical point. So we don't want to lose that. I hope what I said is clear. You're supposed to get all 3 of these critical points. Let's do a sign chart. Three critical points this time. We need to label all of them. Let's say -1 is here, 0 is here, 2 is here. We don't label anything else, just the critical points. And let's say f prime of x, and let's say f of x. And off to the side, let's check points. So we're doing step 3. We need to check one value from each of those intervals. There's 4 intervals this time, right? 3 critical points chops that up into 4 intervals. So f prime needs to be checked at 4 different places, 1 from each interval. We get to choose what numbers we check as long as they're 1 from each. So for the leftmost interval, I decided -2 seemed like a reasonable number. In fact, I'm going to fill out my x values here first. For the second interval, I needed something between -1 and 0. So unfortunately, there's no integers between -1 and 0. So I was like, well, should I pick a decimal or a fraction? I guess we have to. So I chose -0.5. I figured, that's probably going to be the nicest decimal or fraction that I can come up with. All right, in this third interval, we need a number between 0 and 2. I think 1 is the natural choice because usually plugging 1 in to a function is going to be easy. And then for f prime of the fourth interval, we need something bigger than 2, so I chose 3. Remember, we are putting these into f prime of x, not the original f of x, but the f prime of x. So you could put them into this form, 12x cubed, etc., or you could put them into this form, where we pull 12x out. You could actually put them into, you could put them into this form if you want. Right, because like all three of these things are f prime of x, so whichever one seems easiest to you. The factored form might be the easiest one to plug things into, because then you don't actually have to do anything cubed. See what I mean? Well, anyway, I put these in and I got, I'm skipping a little bit of the middle, arithmetic, but I got negative 96, 7.5, negative 24, and 144. And what I really care about is I got negative, positive, negative, positive. Does it matter that this was 7.5 and this was 144? All that really matters is the sign. It goes negative, positive, negative, positive. So let's add that to our sign chart. Negative, positive, negative, positive. So this one does alternate. I told you that that doesn't always happen. They don't always alternate. It's pretty common, though. Underneath, what do we write? F prime being negative means that f of x is decreasing. You can abbreviate it if you want, decreasing. And then on this interval, f is increasing, and then it's decreasing, and then it's increasing. So this is the completed sign chart, and it basically helps us organize all the results we found. And it's pretty cool because now you can see the intervals of increase and decrease, and from this we'll be able to figure out where the local maxima and minima are. So let's do this. Let's write the answers. Okay, increasing. Make sure you indicate what is what. Like, don't just write a bunch of intervals, because then I won't know, okay, which of them are you trying to say are the increasing ones, and which of them are you trying to say are the decreasing ones. Just write the word increasing, Write the word increasing and decreasing. So increasing, it looks like from negative 1 to 0 and 2 to infinity. Those are the two that we wrote increasing. For decreasing, we wrote 2 intervals on the sign chart, and it's going to be negative infinity to negative 1 and 0 to 2. For a local max, I'm going to remind you, when does a local maximum happen? That happens when you switch from increasing and then you're decreasing. So when, reading this from left to right, when does it switch from increasing to decreasing? Decrease, increase, decrease. It switches from increasing to decreasing here at x equals 0. Does it happen anywhere else? Decrease, increase. No. It only happens in that one place that when you go from left to right, you switch from increasing to decreasing. So I'm going to say at x equals 0. For a local minimum, we're looking for a place where it switches from decreasing and then it is increasing as you go from left to right. So we're decreasing, we're decreasing, we're decreasing, and then look, we switch to increasing. So at x equals negative 1 is going to be a local minimum. Let's keep going just to see if there's any more. Yes, look, over here we switch from decreasing to increasing, so at x equals 2. So I'm going to say at x equals negative 1, and x equals 2. This is everything that it asked us for. So I have a couple of things I want to say about this. We answered the problem. Notice that with this problem, I didn't write quite so much. I didn't write as much as I did with that first one. Look at what we wrote. Maybe we can fit the whole thing. Almost. We can almost fit, yeah, just about fit the entire problem on one screen. I just can't fit the question and the problem at the same time, but that's it. That's like half a page. We didn't have to do anything with any inequality symbols. We used the derivative. Yeah, let's quickly review. We found the derivative. We set it equal to 0. That helped us find critical points. We set up the sign chart. It didn't have everything on it originally. It just had the critical numbers labeled. Then we checked one value from each interval. We found negative, positive, negative, positive. We wrote that on the sign chart. We figured out that that means decrease, increase, decrease, increase. And then we kind of carefully read the sign chart to come up with these answers. So we're done with this. I want to show you something, though. Something that I sometimes add to a sign chart. Now, it's not officially a part of a sign chart. I want to be clear that what we wrote here is the completed sign chart. But sometimes I find it helpful to draw like a little picture above it. So when a function is decreasing, it's kind of on a downward trajectory like that, right? You're going downhill. When a function is increasing, it's going upward like that. Let me zoom in on this. When a function is decreasing, it's going downhill again. And then when it's increasing, it's going upward again. So I feel like if we were to graph this function, it would have something like the shape of a letter W. Now, does that help us in any way? The reason why I did this is because I wanted to show you that, look at this. This is where there is a minimum. This is where there is a maximum. And this is where there is a minimum. So that's kind of cool, right? And that's what we wrote in our answers. You know, there is a local minimum at -1. There's a local minimum at x equals 2. Local maximum at x equals 0. But it's because decrease, increase, decrease, increase means the function is something of some kind of shape like this. In the next lesson, I'll give you a preview. In the next lesson, we're going to take some of this information and say, we could probably maybe find a little more information and start to turn this into like a nice graph. Like now I know a rough idea of what it looks like, but if we do a little bit more work, we could find out exactly what this looks like and use this strategy to help us graph the curve, you know, without using a graphing calculator or anything like that. We will become the graphing calculator. Okay, so that was one thing I wanted to say is if you want to, you can do that kind of thing above the sign chart. It's not officially part of the sign chart. It's just kind of scratch work that I do sometimes. Another thing I wanted to say is we found this problem told us to find the x-coordinates of local maxima and local minima, and we did that. X equals 0, x equals this, x equals that. But I just wanted to show you that what if a problem said to find the actual points? Or what if it told you to find the y-coordinates? Let's write some of this underneath so that we're not like writing so much here. So note this problem asked for x-coordinates of the local maxes and mins. We can also find the points. So at x equals 0, what is f? If a problem asks you to do this, you want to be ready for it just in case. What's f? Go back to way back when we had the original function. It was 3 times x to the 4th minus 4 times x to the 3rd minus 12 times, right? So this whole thing, not the derivative, but the original function f. All right, 0 minus 0 minus 0 plus 5 equals 5. So the local max is at the point. We knew it was 0 comma something. When we said that there was a local max at x equals 0, we knew it was 0 comma something. But in fact, now we can say that it's 0 comma 5. Let's do the others. At x equals -1, f of -1 equals all right, it's a little bit more work this time. -1 to the 4th is 1. -1 to the 3rd is -1. -1 squared is 1. So what do I have here? 3 plus 4 is 7. Minus 12 plus 5. Hey, look at that. This winds up being 0. So a local min is at the point -1 comma 0. And we could do the other one. And I'll skip some of this, but at x equals 2, you should find f of 2. You could do this yourself. I actually did this and found -27. So that's a local min at the point 2 comma -27. So, you know, the problem only asked us for x coordinates, but I'm just trying to show you that you can find the y coordinates also if you needed to. Zero comma 5, negative, like we could start to draw a picture already, couldn't we? Using the fact that, you know, the sign chart showed us that this graph probably has overall kind of like a down, up, like a W kind of shape to it. And now we found these specific points. So in the next lesson, we'll be doing that kind of thing and graphing it. I guess you could say that if these are actually the places of the local extrema, then my quick little scratch work picture here is definitely not to scale, because this local minimum is supposed to be at -1 comma 0. And this is supposed to be at 2 comma -27. So this local minimum is supposed to be much lower than the other one. In fact, it's probably an absolute minimum, right? Because if it goes up in this direction, so it's like going down to this, up to this, down really far to -27, and then up. So yeah, we'll talk about that more in the next lesson. But for this lesson, you know, we're mostly interested in the things that I asked for, which is find the intervals of increase and decrease. We did that. Find the x coordinates of local maxima and minima. We did that. And the sign chart is a useful tool. And we basically find critical points and check one value from each interval. All right, one thing that I want to warn you about before we wrap this lesson up, is, you know, the problems in this section, they seem to be multi-part problems. You're given a function f of x, and it asks for lots of information, right? So all of those different pieces of information. So the thing that I want to warn you about is be very careful when you're starting a problem like this. What's the first thing you do in one of these problems? You probably are finding f prime. Find the derivative is usually the first step because you need that to find the critical points. Well, what happens if you make a mistake when you're finding the derivative? All of the rest of the problem is going to be wrong, right? Because you're going to find the wrong critical points, you're going to set up the sign chart wrong, you're going to be checking the wrong things, your maxima and minima might not match up the way they should. So be very careful finding the derivative and finding the critical points, because one mistake in those steps will usually make every part of your answer wrong. But I think by now we're good at finding derivatives. Just don't rush through the derivative step too fast. Just, double check it. Even if it's a polynomial, even if you're like, oh, it's a polynomial, I can just write the derivative down super fast. Double check it, because every part of your answer relies on that being correct. Okay? That's what I wanted to say. So everybody take care. I hope you're doing well, and I will see you soon.